to part 4 of chapter 2. Today we are going to talk about calculations that have to do with concentrations and molarities. So concentration is a way of talking about how much stuff is dissolved in our water. We can use terms like dilute and concentrated to talk about it, and it's especially easy to see whether something's dilute or concentrated based on the color, if we had a colored solution. So if something is dilute, like on this side, that means that we have a very small amount of our solute compared to our solvent. And so our solute, this is the stuff that's dissolved, and oftentimes our solvent will be water. Not always, but a lot of times it will be. And if we're using our water as our solvent, then we are making an aqueous solution. So here we have a very, very small amount of our solute dissolved in our solvent, so we call that dilute. As we add more and more and more of our solute, it becomes more concentrated. So as we add more stuff to our water, we are making a more concentrated solution. And again, it's really easy to see this if our solute is colored in some way. So if we have a concentrated solution, we have a very large amount of our solute compared to our solvent. So this is how we explain it qualitatively. And again, it's really easy to see it if it's got some kind of color to it, but if it doesn't, right, if we're making a bunch of clear solutions, like say, salt water or an acid dissolved in water, then you can't tell just by looking at it whether something is dilute or concentrated. And also, just by saying these words, we don't assign any numbers to them. And as you know in chemistry, we do a lot with mathematics. So our question becomes, okay, well, how much stuff is dissolved in our water, rather than saying a lot or a little, so we need to have some kind of numerical value that goes along with it. One of the most common ways in chemistry to talk about how much stuff is in our water or in our liquid is to talk about it in terms of molarity. And molarity is the number of moles of solute dissolved in 1 liter of solution. So we have an equation here. So molarity is denoted by the capital letter M. Remember, lowercase m means mass, capital M means molarity. And so molarity is the moles of solute over liters of solution. And so make sure that we're using, so this is moles of stuff that's dissolved, like maybe a solid, right? And our liters of solution, this is total, right? Oftentimes it will be the liters of our solvent, just because that is the majority of the volume, but it's technically liters of solution, so be careful there. Liters of both our solute and our solvent added together. So to calculate it, we just take our moles of solute, we divide it by the liters of solution, press enter, there you go. So we often will abbreviate this just moles over liters, just to kind of shorten our equation. So here's an example problem. If we have 2.79 grams of sodium chloride and we are adding it to 22.31 grams of water, what is the molarity of the salt in the solution? And here the problem says, assume the volume of solution is due to the water. So here, our sodium chloride, this is our solute, our water is our solvent, and together they are making up our solution. So the first thing that we're going to need to do is we're going to need to take our grams of our solute and turn that into moles of our solute. So we have 2.79 grams of sodium chloride, and we can turn that into moles just by using our molar mass. So 58.44 grams of sodium chloride per 1 mole. And we can divide those up and we can get our our number of moles, which is 0.0477 moles of sodium chloride. Oftentimes you'll want to drag through a couple more significant figures just so that your number at the end is correct. Since we don't need to round yet, since the whole problem is multiplication and division, you can write it out like this, or you can write it out like this. and just put like a line over the one that is significant. So okay, I'm carrying these extra numbers through for now just to make sure my math is correct at the end, but I need to round to 3 significant figures at the end of this problem. So then we can go ahead and we can calculate molarity. So molarity is going to be moles over liters. And so we need our liters of our solution. So we have our milliliters, we have our grams of water, and our density of water for every 22.31 grams of water, we know we have 22.31 milliliters of water because the density of water is 1 gram per milliliter. So anytime they give you a mass of water, that is going to be the same as the volume of water because of the density. Don't go doing that for other things. Like we can't do that for the salt because the density of salt is not 1 gram per milliliter, it's something else. Here in this problem, it's saying assume the volume of the solution is due to the water. So all of our volume, this liters on the bottom, that's going to be our liters of water. So we can go ahead and convert our milliliters into liters by dividing by 1,000. So now we have our liters of water, and we can go ahead and can convert or calculate our molarity. So we have molarity is moles over liters, so we have 0.0477, right? And like I said, I'm going to carry out a couple more just to keep our answer correct here. So we have moles over our liters of solution, which is going to be our liters of water for this particular problem. So then we can go ahead and divide those up, rounding for 3 significant figures because of the number on the top, and we get 2.14 molar sodium chloride. So that would be the molarity of our solution. So we calculate our moles of solute, divide by liters of solution, and we will come up with our molarity. So practically in lab, the way that we would make this solution is not that a lot of people will get their water, right, and then they'll add their salt, and they'll be like, hey, there's my solution. But that's not actually quite right, because if you think about it, if you have 1 liter of water and you add some salt to it, that volume is going to go above that 1 liter line, right? Even if it's a very small amount, you now don't have 1 liter of solution, you had 1 liter of solvent, right? Which makes, when you add your salt, it'll push that liter of solution over the 1 liter mark. So instead of doing it that way, a better way is to add your solid first. So these are volumetric flasks, and it's a special type of flask, and if you'll look, there's a line up here at the top that is going to measure exactly 1 liter. Not all volumetric flasks measure 1 liter. These ones happen to be 1 liter volumetric flasks. We have ones for 100 milliliters, we have 10 milliliters, we have 1 milliliter, we have 2 liters, you get the idea, right? But they only measure that exact volume. Instead of like a graduated cylinder where you can measure a lot of different volumes, in a volumetric flask you can only measure 1 liter. But they're used for making very, very precise solutions. Because the neck of this flask is so narrow, we can measure volumes really, really precisely. So the way that we make these solutions so that they are accurate is we'll add our salt first. So that's what's happening here. They're pouring in their salt, and that's going to be 1 mole of sodium chloride because we're trying to make 1 molar sodium chloride solution, which means we'll need 1 mole of our solute per 1 liter of solution. So if we're trying to make 1 liter, we need 1 mole. So we add in our 1 mole of sodium chloride, and then we add distilled water or deionized water up until the 1 liter mark. And this way we know we have 1 liter of solution total, right? And then just as a practical note, when you add your water, you don't want to add it completely full yet. You want to add some water and then stir it to dissolve your salt. Because it's really, really hard to stir a very, very full volumetric flask. So if we were actually doing this in lab, we would add our salt, add some water, stir it up until it dissolves, and then add the rest of the water up into the 1 liter mark. And then that's how you make your solution. So then you would have really, really accurately 1 liter of solution rather than 1 liter of solvent. Okay, let's try another problem. This would be another really practical problem. So say that we are trying to prepare a 0.5 molar solution, and I want 1.5 liters of it. Okay, so backtrack, how many grams of sodium chloride are needed to prepare this solution? So what we want to think about is we want to think about using molarity as a conversion factor in our train tracks. Molarity we know is moles over liters. So if we have 0.500 molar, that means that we are using 0.500 moles of sodium chloride per 1 liter of solution. Sorry, I was going for the abbreviation SLN. I got confused halfway through. There we go. 0.5 moles of sodium chloride per 1 liter of solution. That is how we'll think about this molarity, and that will allow us to use it in train tracks as a conversion factor. So for example, we're going to start our train track here with 1.50 liters of solution. Okay, and the reason that we're starting it with the volume instead of the molarity is because molarity is this inherent conversion factor where it's got a top and a bottom, whereas liters do not. So we're going to start with our liters and then use our conversion factor to convert it into moles. So this is how this is going to look. We'll start with 1.50 liters of solution, and then, like I said, we'll use this conversion factor, and we're going to use it as written so that liters of solution will cancel liters of solution down and to the right. So 1 liter of solution will go on the bottom, and 0.5 moles of sodium chloride will go on the top. Then we can use our molar mass of sodium chloride, right, to convert this into grams. Make sure all your units cancel, right? Liters of solution cancels liters of solution. Moles of sodium chloride cancels moles of sodium chloride. We'll multiply the top, divide the bottom, and we will get 43.8 grams of sodium chloride. So in this way, right, this new step is using the molarity as a conversion factor. If we had had moles here, right, we would use our conversion factor upside down so that moles of sodium chloride would cancel moles of sodium chloride. Always make sure your units are canceling down and to the right. But so if you see molarity, think of, it's not just a unit, right? It is also a conversion factor. We're going to do lots of work using molarity as conversion factors in the upcoming lessons. So here's another type of problem, and it's kind of one that you're going to have to think about. This one says, what is the molarity of bromide ions in 50 milliliters of 0.1 molar calcium bromide? And the key here is to know that calcium bromide is an ionic compound. And when we put ionic compounds into water, so let's say we take our calcium bromide and it's a solid, and then I put it into water. When I put it into water, this solid breaks apart because it's an ionic compound. So it's going to break up into 1 calcium ion floating around by itself, and based on the subscripts here, it's going to break into 2 bromide ions. Okay, so that subscript becomes a coefficient in this equation. This is a dissociation equation, right? So this shows how our solid is breaking apart in the water. It will break into 1 calcium ion and 2 bromine ions. So if we started out, right, with 0.100 molar calcium bromide, and I'm trying to figure out how many bromine ions, right, are floating around, those bromide ions, for every 1 calcium bromide, 1 molar calcium bromide, we are going to end up with 2 molar bromide ions. So here I'm using the ratio from this equation, right? For every 1 calcium bromide, I'm getting 2 bromide ions. So you can use this as a mole ratio. You can also use it kind of as like this molarity ratio, right? Because in that molarity, we have moles over liters. We're not changing the volume, right? The volume is going to stay constant the whole time. But what's going to happen is that, that solid is going to break apart into pieces. So for every 1 calcium bromide, we get 2 bromide ions. So the molarity of our bromide ions is actually 0.200 molar bromide. Okay, but the key, like I said, is thinking about this whole breaking apart thing. Had I asked you for the molarity of the calcium ion, that would be the same as the molarity of the calcium bromide, because for every 1 calcium bromide, we're getting 1 calcium. So you need to think about how many of those pieces will be floating around in solution when you are asked a question like this. Let's try another one, slightly different though. This one says, what is the molarity of bromide ions in 200 milliliters of 0.1 molar calcium bromide and 100 milliliters of 0.1 molar calcium chloride mixed together? So what's happening here? We have 1 solution of calcium bromide, we have 1 solution of calcium chloride, we're pouring them together, and I want to know what is the molarity of the bromide ions. This is going to be similar to problems that we're going to do that are in the molarity of leftover ions lesson. So this is going to be kind of a warm-up to that. So just kind of thinking about what we need to solve it. So we're looking for molarity of our bromide. And so what we're going to need to do is we're going to need to find the moles of our bromide, and we're going to divide that by the total volume. Okay, so our first step will be to figure out the molarity of our bromide ions. So we need to deal with stuff about calcium bromide. So that's here. If we have molarity, right, we know molarity is moles over liters. So we're going to, do molarity times liters to figure out our moles. And we're going to do this by way of a train track, similar to how we did in the last problem. So we're going to go ahead and start with our volume here, because that is not a conversion factor, right? We know our molarity is our conversion factor, so we're not going to start with that. We're going to start with our volume. So I'm going to change those milliliters into liters, and we're going to use 0.200 liters of calcium bromide. And using this molarity, right, the molarity is 0.100 moles of calcium bromide per 1 liter of our calcium bromide solution. So for every 1 liter of calcium bromide, we have 0.100 moles of calcium bromide. And then, like we did before, we know that calcium bromide, right, is going to break into 1 calcium ion and 2 bromide ions. So for every 1 calcium bromide, we are getting 2 bromide ions. So then we can go ahead and multiply all of this out, and we can get that we have 0.0400 moles of bromide ions total, right? So this is just coming from our calcium bromide. We use our volume and our molarity to figure out how many moles of bromide ions we actually put in our solution. Then, after we have that, we'll take our moles of bromide ions and we will divide it by the total volume, right? Because our molarity will be in our new solution after they have been mixed together. So we use our initial calcium bromide information to figure out the moles of bromide, and then we'll use our total volume to figure out our liters so that we can figure out our molarity. So our total volume will be the 200 milliliters plus the 100 milliliters, and that will give us 300 milliliters total, or 0.300 liters. So now we can go ahead and calculate the molarity of our bromide ions by doing our moles of bromide over our total volume. So our moles of bromide, we have 0.0400 moles of bromide, and our total volume is 0.300 liters. And then when we divide that up, we will get 0.133 molar bromide. Okay, so this is a different kind of problem than we were asked before. In the problem earlier, we were just asked the molarity of bromide ions in one solution by itself. This question is different because this asks what is the molarity of the bromide ions when we have stuff mixed together. Okay, so that's why we needed to go find the moles of bromide that we put in there, divide it by the total volume, the new volume, and then find the molarity of our bromide ions. Another type of problems that you might see are dilutions. And we do dilutions a ton in chemistry because we'll buy our solutions as stock solutions and we store them like as concentrated, kind of like if we buy an acid, right? We're going to buy a really, really concentrated acid and then we will dilute it down to a given molarity based on what kind of reaction we're going to do. Otherwise, if we were to buy say 3 molar hydrochloric acid and 1 molar hydrochloric acid and 0.1 molar hydrochloric acid, we would have to store all of these different molarities of solutions, and that's, from a practical standpoint, going to take up a ton of space. Also, to buy all of these dilute solutions actually ends up being really expensive because you're paying someone else to dilute your solution for you. So oftentimes we will buy stock solutions and then dilute them ourselves right before we use them in a given reaction. And in this way, like I said, you're going to save yourself money. You're also saving space in your lab. And it's just more practical that way. It's quick and easy to dilute a solution to whatever molarity you want to use it for. And so to make our solutions of lower concentrations from the stock solution, what we're going to do is we just add more solvent, right? We're going to add more water, or add more of whatever solvent we're using. And the key here is that the amount of solute doesn't change, just the volume of solution. So this is in essence, what we were doing here is we were diluting our bromide ions. It just kind of ended up that what we were adding was another solution rather than just water. Here we would just add water. But the key is that the moles don't change. So if we think about molarity is equal to moles over liters. To solve for moles, right, we rearrange this and we get molarity times liters, or, molarity times volume, essentially. And that's what we're working with down in this equation, is that the moles before dilution are going to equal our moles after dilution. The things that are changing are the molarity and the volume, but the number of moles of your solute doesn't change, right? You're not adding or subtracting any moles of hydrochloric acid, you're just changing the amount of water. So since we're just changing the amounts of water, the molarity and the volume before is going to be, if you multiply those together and get moles, that will equal our molarity and volume after. So we have this equation, this M1V1 equals M2V2. And so one side we'll call our stock solution, and the other side we can call our dilute solution. And I usually make it as the ones as stock and the twos as dilute, but you can do it however you want, as long as you denote that one side is your stock solution, one side is your dilute solution. One side is essentially before you dilute it, and the other side is after. Okay, and this is how we will go about, figuring how much water we need to add, or how much of our stock solution we need to start with to make a given concentration, right? We'll use this M1V1 equals M2V2. And the way that a problem will show up is it will look like this. What volume of stock hydrochloric acid is needed to prepare 250 milliliters of 3.0 molar hydrochloric acid solution? So in this scenario, we're assuming that we're going to do a reaction. We need 250 milliliters of 3 molar hydrochloric acid. It says so in the procedure. So we go, into our stock room and we get out our stock solution of hydrochloric acid. And we need to figure out how much hydrochloric acid we're going to use, and then add a bunch of water to, figure out to make this solution. So we use our M1V1 equals M2V2. And again, like I said, I'll usually use the ones on the left as the stock solution and the ones on the right as the dilute solution, but you could do it vice versa if you like to. So then we plug in what we know. We have 11.6 molar, right? That's our stock volume, and we don't know how much, our stock molarity, and we don't know how much we're going to use to make our solution. But we know we want 3 molar hydrochloric acid, and we want 250 milliliters or 0.250 liters. It's important to know you can do these problems in liters or in milliliters as long as you are consistent, right? So like if this one is liters, then this one needs to be liters. If this one's milliliters, then this one can be milliliters. Either is fine, just as long as you're not changing units in the middle of your problem. So now we can go ahead, we can rearrange. We get liters will be, our molarity, our dilute divided by our stock information, and we can get that we will need 0.065 liters or 65 milliliters of hydrochloric acid. So the way that we would actually go about making this, we would use 65 milliliters of hydrochloric acid and the rest of the solution, right, the other 185 milliliters, that's going to be water. And just from a practical standpoint, again, whenever you're diluting an acid, you always want to add your water first and then your acid. Never put water into acid. It can make it pop and spray you with acid. So always add your water first, then add some acid, and then you can add, the rest of your water later, but never just put water into acid. It is not going to go well. Let's try another one. So this one says if I have 340 milliliters of 0.5 molar sodium bromide, what will the concentration be if I add 560 milliliters more water to it? So be careful on the wording here, okay? We have 340 milliliters of our sodium bromide. This is going to be our stock, okay? And then our dilute solution, you'll see that we are adding water to this. So our volume here is not going to be the 560 milliliters. It's actually going to be 340 plus 560 because we need the total volume of our dilute solution to do this calculation. So M1V1 equals M2V2. So we have our molarity is 0.5 molar for our stock. We have 340 milliliters, and again, like I told you, you can do this in milliliters or you can do it in liters as long as you are consistent. And so our second molarity, that's what we're trying to find, right? Our dilute molarity, and our volume here is going to be that 340 plus 560. And this gets us 900 milliliters, but if you'll look, we need to have two significant figures here, right? We need to have this, that place be significant. So I'm just going to put a line over here, or you can write it as 9.0 times 10 to the second. Either way, so that you keep your significant figures. And then if we go ahead and multiply, divide, do all the things, rearrange, solve for M2, we are going to get that M2 is 0.2 molar sodium bromide. Okay, so there you have it. Nice, easy ways to do dilutions. M1V1 equals M2V2. And that is the end of today's lesson. So today we talked about molarity as a way of talking about concentration, and I showed you a bunch of different calculations that you can do with molarity. Moving forward in this class, we will use molarity a ton as a conversion factor in train tracks, in dilutions, so you need to get really, really good at molarity. So do a lot of your practice problems, work on that Chapter 4 lecture worksheet, and as always, if you have any questions, please send them to me, and I'll talk to you next time.